Step into an ancient emerald green world. The vibrant colors and the earthy fragrance of tangled vegetation are so enchanting that it takes a moment to notice something is off. It's unnervingly quiet. The usual chorus of birds and the rustle of mammals is missing. An ominous sign. This land is dying, its fate sealed by the end of an ice age. Rising seas and the lush expanse beneath your feet will soon rest 30 meters below the Pacific surface. Many migratory species have fled, seeking refuge to continue their battle for survival in a warming, shrinking world. Those bound by their roots, however, are doomed to perish. What happened here, and what can the ancient past, locked within melting polar ice, teach us? These questions are urgent, for the melting is happening again. What forces are driving today's ice caps to retreat? How will this reshape Earth's most powerful climate systems? And what secrets, both ancient and perilous, lie hidden in the thawing ice? Today, we delve into the incredible significance of ice, a substance that shapes our world and its future. We'll explore the hidden dangers it holds and imagine a wetter Earth, one that may already be taking form. In our past videos, we're captivated by phenomena so vast they challenge our understanding. From the sprawling Andromeda galaxy, 2.5 million light-years away, to the history recorded in every ice layer beneath our feet. We seek to connect with the incomprehensible. Yet, curiously, looking just 80 years into Earth's future feels harder to grasp. But it's vital. What we do today will define tomorrow. Let's start our journey with ice, a truly remarkable substance. It holds immense amounts of energy. To put it into perspective, the energy stored in today's advanced electric cars, capable of propelling tons of metal at speeds over 160 kilometers per hour, would barely melt the ice that could fit in their back seats. This immense energy storage is why ice has been crucial to the stability of the Earth's climate over the past 12,000 years during the Holocene epoch. This stability, which acted as a buffer against extreme temperature swings, was crucial to the rise of humanity. The stable climate allowed agriculture to flourish, laying the foundation for civilization. The Antarctic ice cap began to form 37 million years ago, while the Arctic ice cap appeared 2.7 million years ago, about as old as the light reaching us from Andromeda today. These ice caps remain essential for maintaining the Earth's delicate climate balance. Their size has historically been influenced by the Earth's position and tilt in the solar system, which are governed by Milankovitch cycles, planetary motions that change the energy the Earth receives. As we unravel the mysteries of Earth's icy history, we gain insight into the forces shaping our planet's future. Join us as we explore the legacy of ice and face the urgent challenges of a warming world. Together, let's connect the past, present, and future, because what we do now matters more than ever. According to the natural rhythm of Milankovitch cycles, polar ice should be increasing, signaling the approach of an ice age. Sea levels should be falling as the ice caps thicken. Instead, we are seeing the opposite. Polar ice is melting at an accelerating rate, absorbing massive amounts of energy. If all the ice were to melt, sea levels could rise by a staggering 70 meters, putting every coastal city on Earth underwater. Fortunately, such a catastrophic scenario is highly unlikely. But understanding how much sea level rise we can expect is crucial for planning and protecting our ecosystems. To make these predictions, we need to understand why the ice is melting so fast. We know that the release of greenhouse gases is driving modern global warming, overwhelming the cooling trends predicted by Milankovitch cycles. This warming is accelerating the melting of the ice caps and raising sea levels. However, the relationship between greenhouse gases and temperature hasn't always been the same. Ice core records from Antarctica show a surprising reversal in the past. Rising temperatures triggered increases in CO2 levels, not the other way around. Does this contradict current science? Not at all. The relationship is cyclical, with each influencing the other. The key difference is what triggers the process. We are seeing this interplay today as warming temperatures thaw the Arctic permafrost, releasing long-buried carbon reserves. This release of greenhouse gases further accelerates warming in a self-reinforcing feedback loop. The intricate mechanism linking greenhouse gases, temperature, and ice reveals a complex climate system. Greenhouse gases trap infrared radiation, trapping heat in the Earth's atmosphere and oceans. The oceans, with their immense mass, 1.34 quintillion tons compared to the atmosphere's 5.5 quadrillion tons, absorb about 90% of this extra energy. This extra energy doesn't stay evenly distributed. Heat naturally flows from warmer areas to colder ones, and the Earth's poles, with their strong temperature gradients, become focal points for this energy transfer. Ocean currents play an important role in transporting heat to the poles, intensifying the warming there. Water is an excellent energy carrier because of its high density and heat capacity. This is why water is used both as a coolant in engines and as a heating medium in homes. Air, on the other hand, with its lower density and heat capacity, is a poor conductor of heat, which is why it works well as an insulator. This difference is striking. You can sit for minutes in a 90-degree Celsius sauna, but dipping a fingertip in water at the same temperature would cause immediate pain. The ocean's ability to store and transfer energy makes it a key player in polar ice melt. Melting ice isn't just about rising temperatures. Other factors are also important. One is the albedo, or reflectivity, of the ice. Clean, white ice reflects most of the sun's rays. But when soot or particulates darken its surface, it absorbs more solar energy, accelerating melting. Efforts to improve air quality by reducing particulate pollution have a dual effect. While cleaner air reduces the amount of soot that lands on the ice, slowing direct melt, it also allows more sunlight to reach the Earth's surface. This amplifies the greenhouse effect, making the situation more complex. Let's take a closer look at how the oceans contribute to polar ice melt, especially in vulnerable areas such as the West Antarctic ice sheet, which contains several types of ice. Sea ice, which forms and melts seasonally, can double the size of Antarctica in winter. Its direct melting into the ocean has a minimal effect on sea level, a few centimeters at most, but its real importance lies in its protective role. Sea ice insulates the ocean from atmospheric warming, keeping the air above it colder and drier. Its bright, reflective surface also reflects much of the sunlight back into space, preventing further warming. When sea ice levels are low, the underlying ice shelves are exposed to both atmospheric and oceanic heat, making them vulnerable. Ice shelves are floating extensions of land-based ice sheets. Some, such as the Ross and Ron-Filchner shelves, are larger than the UK. These shelves act as barriers, holding back huge amounts of land-based ice. Warm seawater melts the underside of these shelves, weakening them and leading to calving, where huge icebergs, sometimes the size of cities, break off and drift into the ocean. While the ice shelves themselves contribute little to sea level rise because they're already floating, their retreat exposes the land-based ice sheets behind them. Once the protective ice shelves shrink, glaciers and ice streams, massive rivers of ice, flow more rapidly into the ocean. These ice streams are far from modest. Some are as wide as the Amazon River's mouth, hundreds of kilometers long, and several kilometers deep. At the heart of the system is the colossal Antarctic ice sheet. Unlike floating ice, the melt from this land-based ice directly contributes to rising sea levels. Under natural conditions, the polar ice caps experience a balance between ice formation and loss. Fresh snowfall and ice formation replenish the ice sheets, while sea ice melts, ice shelves calve, and glaciers flow toward the ocean. But today, this balance is broken. The ice caps are losing ice faster than snowfall can replenish it. Greenhouse gases have introduced additional energy into the oceans and atmosphere, committing Earth to significant ice sheet loss. Can we calculate how much sea levels will rise from melting ice? It's not as straightforward as simply adding the volume of melted ice to the ocean. The complexities of ocean dynamics, thermal expansion, and regional variations in melt rates make this a far more intricate challenge. What we do know is that Earth's polar ice sheets are shrinking, and their continued loss will profoundly reshape our planet. Accurately predicting future sea level rise requires understanding several interconnected factors. While we often think of Earth's crust as solid and immovable, it is surprisingly flexible under immense force. As ice melts and reduces the weight on the underlying continental plates, these land masses rise, known as isostatic rebound. Simultaneously, coastal areas near the equator sink due to the redistribution of weight, causing localized sea level changes. However, the biggest contributor to sea level rise so far hasn't been melting ice but thermal expansion. As the ocean absorbs heat, its volume increases. In fact, almost half of the observed sea level rise since the Industrial Revolution is due to this process. This process is relatively predictable, but the addition of cold, fresh water from melting ice has more unpredictable consequences. The Earth's climate systems are highly interconnected and sensitive to dramatic changes known as tipping points. Like a precarious game of Jenga, removing a critical piece can lead to rapid and irreversible collapse. One potential tipping point within our lifetime is the slowing or collapse of the Atlantic Meridional Overturning Circulation, AMOC, a vital oceanic conveyor belt that redistributes heat around the globe. The AMOC is part of the larger thermohaline circulation system, which is driven by differences in temperature thermo and salinity haline. It carries warm tropical waters north along the eastern United States and across to Europe, contributing to the relatively mild climate of northern Europe despite its high latitude. When this warm water reaches the Arctic, it cools and forms sea ice, leaving behind saltier, denser water that sinks to the ocean floor and flows south to complete the cycle. The Greenland ice sheet releases huge amounts of fresh water into the northern Atlantic, diluting the salty water and reducing its density. This disrupts the sinking process that drives the AMOC. The result? A slowdown in circulation, like a bottleneck on a motorway causing traffic to back up. For the east coast of the United States, this slowdown leads to rising sea levels. In Europe, coastal waters may retreat, but the consequences are far more severe. Reduced ocean heat transport could plunge northern Europe into a much cooler climate. The UK, for example, could experience a 10 degrees Celsius drop in average temperatures, making it colder than present-day Iceland. The effects of a weakened AMOC are global. Rainfall patterns would shift dramatically, turning some regions into rainforests and others into deserts. This would severely disrupt ecosystems and food production, with dire consequences for human populations. When the Greenland ice sheet melts, it's not just water that is released. Trapped in the ancient ice are microorganisms and pathogens that haven't existed on Earth for hundreds of thousands of years. Introducing such organisms into modern ecosystems could upset delicate balances, especially when pathogens are involved. While most microbes may be harmless, it only takes a black swan event to cause global upheaval, as we saw in 2020. The deeper the permafrost thaws, the greater the risk. Ancient pathogens have undergone significant evolutionary changes, making modern ecosystems and humans less prepared to deal with them. The world as we know it is undergoing profound changes. Ice, nature's time capsule, holds an unparalleled record of Earth's history. By studying it, we uncover not only our planet's history, but also our own. As the ice melts, it reveals echoes of past environmental missteps, reopening chapters we thought closed. Trapped within are chemicals once unleashed by humanity, substances that can now re-enter ecosystems and exacerbate existing challenges. Chlorofluorocarbons, CFCs, long buried in ice, could again damage the ozone layer and accelerate polar ice loss. Chlorinated pesticides, some of which have been banned for decades, may re-emerge with time in the ice, potentially making them more toxic. Even vaporized lead from the era of leaded petrol will re-enter the environment as these frozen layers dissolve. This chemical resurgence is increasing the stress on an already fragile global ecosystem, pushing it ever closer to an invisible tipping point. If current trends continue, the world could look very different by 2100. Projections suggest an average sea level rise of 0.5 meters by the end of the century, a figure that may seem modest at first glance. A global map may show little change to coastlines, but the impact lies not in the averages, but in the extremes. Black swan events, intense storms, catastrophic floods, and relentless heat waves will shape human behavior and survival. By 2100, a population equivalent to that of the United States today will face regular coastal flooding. This raises critical questions. Where will these displaced people go? How will their migration reshape societies? And what will become of our way of life? The Earth's rich diversity of species and cultures is a testament to adaptability. Life, including humankind, has demonstrated its resilience time and again, evolving and thriving under new conditions. While the melting ice is a stark reminder of the environmental damage done since the Industrial Revolution, it also carries a message of hope. Throughout history, humanity has demonstrated its ability to unite and act when faced with challenges that threaten our collective well-being. We've made transformative changes before, and we can do it again. The road ahead may call for groundbreaking solutions, engineering feats designed to alleviate the strain on Earth's ecosystems. Such innovations might seem daunting, as if they require the genius of an extraordinary inventor. But consider this. That inventor could be you. Our future is not set in stone. It remains in our hands, shaped by the decisions we make today. With creativity, collaboration, and a commitment to change, we have the power to build a world that ensures the well-being of both the planet and future generations. Together, we can rise to the challenge, and together we can make a difference. The ice is melting, the clock is ticking, and the choices we make now will determine whether we face these challenges prepared or overwhelmed. The question isn't just what lies beneath the ice, it's what will we do about it. If this journey into the depths of the Antarctic has intrigued or inspired you, don't forget to like, share, and subscribe for more explorations into the mysteries of our planet and beyond. And let me know in the comments, what do you think is the most pressing discovery beneath the ice? Until next time, stay curious, stay informed, and together, let's continue to explore the unknown.